Hello viewers, welcome to my channel Online Biology Tutorials. In today's live, we will be reading chapter 4, Carbon and its Compound, taken from NCERT Class 10 Science. This is being followed in CBSE board. In case you are interested in hearing the audio of first 3 chapters, a playlist has already been uploaded on my channel. I hope the screen is clear to everybody. So let's start with the reading of chapter 4, Carbon and its Compounds. In the last chapter, we came to know many compounds of importance to us. In this chapter, we will study about some more interesting compounds and their properties. Also, we shall be learning about carbon, an element which is of immense significance to us in both its elemental form and in the combined form. Activity 4.1. Make a list of 10 things you have used or consumed since the morning. Compile this list with the list made by your classmates and then sort the items into the adjacent table. If there are items which are made up of more than one material, put them into both the relevant columns of the table. So you need to categorize into the things made of metal, things made of glass or clay, or others. So let's begin with the reading main part. Look at the items that come in the last column of the above table filled by you. Your teacher will be able to tell you that most of them are made up of compounds of carbon. Can you think of a method to test this? What would be the product if a compound containing carbon is burnt? Do you know of any test to confirm this? Food, clothes, medicines, books, or many of the things that you listed are all based on this versatile element carbon. In addition, all living structures are carbon based. The amount of carbon present in the Earth's crust and in the atmosphere is quite meager. The Earth's crust has only 0.02% carbon in the form of minerals like carbonates, hydrogen carbonates, coal, and petroleum. And the atmosphere has 0.03% of carbon dioxide. In spite of this small amount of carbon available in nature, the importance of carbon seems to be immense. In this chapter, we will know about the properties of carbon which make carbon so important to us. 4.1 Bonding in carbon. We have studied the properties of ionic compounds. We saw that ionic compounds have high melting and boiling points and conduct electricity in solution or in the molten state. Hi Tanu, welcome to the live reading by Online Biology Tutorials. We also, next page please. So, how the nature of bonding in ionic compounds explains these properties. Let us now study the properties of some carbon compounds. Most carbon compounds are poor conductors of electricity, as we have seen in chapter 2. From the data given in table 4.1 on the boiling and melting points of the carbon compounds, we find that these compounds have low melting and boiling points as compared to ionic compounds, chapter 3. We can conclude that the forces of attraction between the molecules are not very strong. Since these compounds are largely non-conductors of electricity, we can conclude that the bonding in these compounds does not give rise to any ions. So if you look at table 4.1, melting and boiling points of some compounds of carbon are given. These are acetic acid, chloroform, ethanol, methane. Melting point among all the 4 given compounds is possessed highest by acetic acid, and the boiling point of acetic acid is also the highest. Make sure that you learn the unit. It is given in Kelvin, which is the SI unit of temperature. In class 9, we learned about the combining capacity of various elements and how it depends on the number of valence electrons. Let us now look at the electronic configuration of carbon. The atomic number of carbon is 6. What would be the distribution of electrons in various shells of carbon? How many valence electrons will carbon have? We know that the reactivity of elements is explained as their tendency to attain a completely filled outer shell, that is, attain noble gas configuration. Elements forming ionic compounds achieve this by either gaining or losing electrons from the outermost shell. In the case of carbon, it has 4 electrons in the outermost shell and needs to gain or lose 4 electrons to attain noble gas configuration. If it were to gain or lose electrons, it could gain 4 electrons, forming C4 minus anion, but it would be difficult for the nucleus with 6 protons to hold on to 10 electrons, that is 4 extra electrons. It could lose 4 electrons forming C4 plus cation, but it would require a large amount of energy to remove 4 electrons, leaving behind a carbon cation with 6 protons in its nucleus holding on to just 2 electrons. Carbon overcomes this problem by sharing its valence electrons with other atoms of carbon or with atoms of other elements. Not just carbon, but many other elements form molecules by sharing electrons in this manner. The shared electrons belong to the outermost shell of both the atoms and lead to both atoms attaining the noble gas configuration. Before going on to compounds of carbon, let us look at some simple molecules formed by the sharing of valence electrons. The simplest molecule formed in this manner is that of hydrogen. As you have learned earlier, the atomic number of hydrogen is 1. Hence, hydrogen has 1 electron in its K shell and it requires 1 more electron to fill the K shell. So, two hydrogen atoms share their electrons to form a molecule of hydrogen H2. This allows each hydrogen atom to attain the next page. I hope the screen is clear. Electronic configuration of the nearest noble gas. Helium, which has 2 electrons in its K shell. We can depict this using dots or crosses to represent valence electrons as shown in figure 4.1. The shared pair of electrons is said to constitute a single covalent bond between the two hydrogen atoms. A single covalent bond is also represented by a line between the two atoms as shown in figure 4.2. Hi Rekha Rani, welcome to my channel Online Biology Tutorials. We are doing the live reading of chapter 4 Carbon and its compound class 10th. The atomic number of chlorine is 17. What would be its electronic configuration and its valency? Chlorine forms a diatomic molecule, Cl2. Can you draw the electron dot structure for this molecule? Note that only valence shell electrons need to be depicted. In the case of oxygen, we see the formation of a double bond between two oxygen atoms. This is because an atom of oxygen has 6 electrons in its L shell. The atomic number of oxygen is 8 and it requires 2 more electrons to complete its oxide. So each atom of oxygen shares 2 electrons with another atom of oxygen to give us the structure shown in figure 4.3. The 2 electrons contributed by each oxygen atom give rise to two shared pair of electrons. This is said to constitute a double bond between the two atoms. Can you now depict a molecule of water showing the nature of bonding between one oxygen atom and two hydrogen atoms? Does the molecule have single bonds or double bonds? What would happen in the case of diatomic molecule of nitrogen? Nitrogen has the atomic number 7. What would be its electronic configuration and its combining capacity? In nitrogen contributes 3 electrons. In order to attain an octet, each nitrogen atom in a molecule of nitrogen contributes 3 electrons, giving rise to 3 shared pair of electrons. This is said to constitute a triple bond between the two atoms. The electron dot structure of N2 and its triple bond can be depicted as figure 4.4. A molecule of ammonia has the formula NH3. Can you draw the electron dot structure for this molecule showing how all 4 atoms achieve noble gas configuration? Will the molecule have single, double, or triple bonds? Let us now take a look at methane, which is a compound of carbon. Methane is a widely used fuel and is common component of biogas and compressed natural gas CNG. It is also one of the simplest compounds formed by carbon. Methane has a formula CH4. Hydrogen, as you know, has a valency of 1. Carbon is a tetravalent because it has 4 valence electrons. In order to achieve noble gas configuration, carbon shares 3 these electrons with 4 atoms of hydrogen as shown in figure 4.5. Such bonds, which are formed by the sharing of an electron pair between two atoms, are known as covalent bonds. Covalent bonded molecules are seen to have strong bonds within the molecule, but intermolecular forces are weak. This gives rise to the low melting and boiling points of these compounds. Since the electrons are shared between atoms and no shared particles are formed, such covalent compounds are generally poor conductors of electricity. Allotropes of carbon. The element carbon occurs in different forms in nature with widely varying physical properties. Both diamond and graphite are formed by carbon atoms. The difference lies in the manner in which carbon atoms are bonded to one another. In diamond, each carbon atom is bonded to four other carbon atoms, forming a rigid three-dimensional structure. In graphite, each carbon atom is bonded to three other carbon atoms in the same plane, giving a hexagonal array. One of these bonds in a double bond, and thus the valency of carbon is satisfied. Graphite structure is formed by the hexagon arrays being placed in layers one above the other. So in the figure, structure of diamond is shown here, graphite, and then the structure of C60 Buckminster fullerene. These two different structures result in diamond and graphite having it is smooth and slippery. Graphite is also a very good conductor of electricity, unlike other nonmetals that you studied in the previous chapter. Diamonds can be synthesized by subjecting pure carbon to a very high pressure and temperature. These synthetic diamonds are small but are otherwise indistinguishable from natural diamonds. Fullerenes form another class of carbon allotropes. The first one to be identified was C60, which has carbon atoms arranged in the shape of a football. Since this looked like the geodesic dome designed by the US architect Buckminster Fuller. The molecule was named as fullerene. In text question, question number 1, what would be the electron dot structure of carbon dioxide, which has the formula CO2? Question number 2, what would be the electron dot structure of a molecule of sulfur, which is made up of 8 atoms and sulfur? Hint, the 8 atoms of sulfur are joined together in the form of a ring. Next page. 4.2 Versatile nature of carbon. We have seen the formation of covalent bonds by the sharing of electrons in various elements and compounds. We have also seen the structure of a simple carbon compound, methane. In the beginning of the chapter, we saw how many things we use contain carbon. In fact, we ourselves are made up of carbon compounds. The number of carbon compounds whose formula are known to chemists was recently estimated to be in millions. This outnumbers by a large margin the compounds formed by other elements put together. Why is it that this property is seen in carbon and not other elements? The nature of the covalent bond enables carbon to form a large number of compounds. Two factors noticed in the case of carbon are 1. Carbon has the unique ability to form bonds with other atoms of carbon, giving rise to large molecules. This property is called catenation. These compounds may have long chains of carbon, branch chains of carbons, or even carbon atoms arranged in rings. In addition, carbon atoms may be linked by single, double, or triple bonds. Compounds of carbon which are linked by only single bonds between the carbon atoms are called saturated compounds. Compounds of carbon having double or triple bonds between their carbon atoms are called unsaturated compounds. Hi, Samrat. The purpose of this live stream is that I am creating a playlist of audio chapters of class 10 NCERT Science. An explanatory live will commence next week. So if you feel like, you can subscribe so that you can get the notifications. No other element exhibits the property of catenation to the extent seen in carbon compounds. Silicon forms compound with hydrogen which have chains of up to 7 or 8 atoms, but these compounds are very reactive. The carbon-carbon bond is very strong and hence stable. This gives us the large number of compounds with many carbon atoms linked to each other. Now point number 2. Since carbon has a valency of 4, it is capable of bonding with 4 other atoms of carbon or atoms of some other monovalent element. Compounds of carbon are formed with oxygen and hydrogen, sulfur, chlorine, and many other elements, giving rise to compounds with specific properties which depend on the elements other than the carbon present in the molecule. Again, the bonds that carbon forms with most other elements are very strong, making these compounds exceptionally stable. One reason for the formation of strong bonds by carbon is its small size. This enables the nucleus to hold on the shared pairs of electrons strongly. The bonds formed by elements having bigger atoms are much weaker. Next page, please. So, I hope it is clear. So, I can read it like this. This way, it will be clear to you. More to know, organic compounds. The two characteristic features seen in carbon, that is tetravalency and catenation, put together give rise to a large number of compounds. Many have the same non-carbon atom or group of atoms attached to different carbon chains. These compounds were initially extracted from natural substances, and it was thought that these carbon compounds or organic compounds could only be formed within a living system. That is, it was postulated that a vital force was necessary for their synthesis. Frederick Wohler disapproved this in 1828 by preparing urea from ammonium cyanate. But carbon compounds, except for carbides, oxides of carbon, carbonate, and hydrogen carbonate, salts, continue to be studied under organic chemistry. Next topic, 4.2.1, and this is saturated and unsaturated carbon compounds. We have already seen the structure of methane. Another compound formed between carbon and hydrogen is ethane with a formula of C2H6. In order to arrive at the structure of simple carbon compounds, the first step is to link the carbon atoms together with a single bond, figure 4.6a, and then use the hydrogen atoms to satisfy the remaining valencies of carbon, figure 4.6b. For example, the structure of ethane is arrived in the following steps. It is C-C, means a bond is there in between. So carbon atoms are linked together by a single bond. Three valencies of each carbon remain unsatisfied. So each is bonded to three hydrogen atoms, giving, so this is how each carbon is bonded to three. So here the central carbon 1, 2, 3, and this carbon 1, 2, 3. The electron dot structure of ethane is shown in figure 4.6c. This one. Can you draw the structure of propane, which has the molecular formula C3H8 in a similar manner? You will see that the valencies of all the atoms are satisfied by single bonds between them. Such carbon atoms are called saturated compounds. These compounds are normally not very reactive. However, another compound of carbon and hydrogen has the property of C2H4, which is ethene. How can this molecule be depicted? We follow the same stepwise approach as above. Carbon-carbon atoms linked together with a single bond, as the step 1, it has already been shown. We see that one valency per carbon atom remains unsatisfied, that is shown to you in step 2. This can be satisfied only if there is a double bond between the two carbons, which is shown to you in step 3. Now move to the next page, please. The electron dot structure for ethene is given in figure 4.7, this side. Yet another compound of hydrogen and carbon has the formula C2H2, which is ethine. Can you draw the electron dot structure for ethine? How many bonds are necessary between the two carbon atoms in order to satisfy their valencies? Such compounds of carbon having double or triple bonds between the carbon bonds are known as unsaturated carbon compounds, and they are most reactive than the saturated carbon compounds. 4.2.2 chains, branches, and rings. In the earlier section, we mentioned that the carbon compounds methane, ethane, and propane, containing respectively 1, 2, and 3 carbon atoms. Such chains of carbon atoms can contain many more carbon atoms. The names and structures of 6 of these are given in table 4.2. So here is the table 4.2, which is giving you the formula and structures of saturated compounds of carbon and hydrogen. So they have given you the hydrocarbon homologous series of methane, ethane, propane, butane, pentane, hexane. Always remember, methane will just be having one carbon. Ethane will be characterized by two carbons. So whenever you are reading the word prop, it means three. But, four. Pent, five. Hex, as the name itself is telling you, 6. So the general formula is for methane it is CH4, but another time when you're moving to the next member of this homologous series, you need to add CH2. So when you will add CH2 to CH4, it will become C2H6. Similarly, again, while moving from methane to propane, you need to add CH2, so it will become C3H8. Again, to propane, you can add one CH2 and find it out on your own what it becomes, right? So it will always sit with a notebook and a pen, and this will help you in making the series. There is no need of rote learning at all in this. So one is for methane, two C2 for ethane, C3 for propane, and the basic series is starting from methane. Every time to move to the next member you have to add CH2, and how easy it is to draw. It's carbon in between, then all the four sides hydrogen, carbon in between, then this fourth one is related to another carbon. So every time the valency of carbon should be satisfied, right? So you need to draw all these structures. No need to learn. By practicing, you will be able to do so. I am starting with a live series on it in the coming week. You can subscribe so that you can get the notification if it is of your help. But let us take another look at butane. If we make the carbon skeleton with four carbon atoms, we see that two different possible skeletons are there. One is the straight one, this is the branched one, filling the remaining valences with hydrogen. So this straight will was already being shown in the previous table, and this is how we are completing the valency of carbon by writing hydrogen along its side. So see here we have not written hydrogen at the top because the valency is already being fulfilled. 1, 2, 3, 4. See this carbon, 1, 2, 3, 4. Here also 1, 2, 3, 4. Every time the valency is satisfied, whether we are making the branched one or the straight one. We see that both these structures have the same formula, C4H10. Such compounds with identical molecular formula but different structures are called structural isomers. In order to straight and balance carbon chains, some compounds have carbon atoms arranged in the form of a ring. For example, cyclohexane has the formula of C6H12 and the following structure. So here the carbon has been arranged in a ring. Six carbons are being arranged in a ring, and then hydrogen has been put to satisfy the valency of carbon. So this is cyclohexane. Why is hexane? Because six carbons. Why cyclo? Because it is in the form of a ring. Can you draw the electron dot structure for cyclohexane? Straight chain, branch chain, and cyclic carbon compounds all may be saturated or unsaturated. For example, benzene C6H6 has the following structure. So this is how benzene has been shown to you. It is an aromatic compound. All these carbon atoms which contain only carbon and hydrogen are called hydrocarbons. Among these, the saturated hydrocarbons are known as alkanes. The unsaturated hydrocarbons which contain one or more double bonds are called alkenes. These containing one or more triple bonds are called alkynes. 4.2.3, will you be my friend? Carbon seems to be a friendly element. So far, we have been looking at compounds containing carbon and hydrogen only, but carbon also forms bonds with other elements such as halogen, oxygen, nitrogen, and sulfur. I hope the screen is clear. In a hydrocarbon chain, one or more hydrogens can be replaced by these elements such that the valency of the carbon remains satisfied. In such compounds, the element replacing hydrogen is referred to as heteroatom. These heteroatoms are also present in some group as given in table 4.3. These heteroatoms and the group containing these confer specific properties to the compound regardless of the length and nature of the carbon chain, and hence are called functional groups. Some important functional groups are given in the table 4.3. Free valencies or valencies of the groups are shown by the single line. The functional group is attached to the carbon chain through this valency by replacing one hydrogen atom or atoms. So this table is very, very important. So chlorine, Cl, Br, bromine, they are known as haloalkanes. So in case hydrogen is there in the main molecule, we will be replacing that with Cr in case it is chloroalkane. We will be writing Br if it is bromoalkane. So alcohol, if it is there in any of the chemical substance, we it is must to have OH in it. I hope you all are aware about sanitizers. They contain ethyl alcohol. So ethyl alcohol is represented as C2H5OH that you must have read in respiration chapter as well. If any substance has aldehyde, the functional group is CHO. If it is ketone, then it is C double bond O. But this C double bond O has to come in between. Here also C will be there, here also C will be there. Anything that has carboxylic acid, that will be written as COOH. You have read names of so many acids in chapter 2, acid, bases, and salt, like methanoic acid, oxalic acid. So any acid, acetic acid, it must have COOH group at the end. Let's move on to the homologous series now. 4.2.4 homologous series, you have seen that carbon atoms can be linked together to form chains of varying lengths. These chains can be branched also. In addition, hydrogen atom or other atoms on these carbon chains can be replaced by any of the functional groups that we saw above. The presence of a functional group such as alcohol decides the properties of the carbon compounds regardless of the length of the carbon chain. For example, the chemical properties of methanol CH3OH, ethyl alcohol C2H5OH, propanol C2H5OH, or butanol or butyl alcohol C4H9OH are all similar. Hence, such a series of compounds in which the same functional group substitutes for hydrogen in a carbon chain is called a homologous series. Let us look at the homologous series that we saw earlier in table 4.2. If you look at the formula of successive compounds, say CH4 and C2H6, they differ by a CH2 unit. C2H6 and C3H8, they differ by CH2 unit. What is the difference between the next pair, propane and butane? Can you find out the difference in molecular masses between these pairs? The atomic mass of carbon is 12U and the atomic mass of hydrogen is 1U. Similarly, take the homologous series for alkenes. The first member of the series is ethene, which we have already come across the section 4.2.1. What is the formula of ethene? The succeeding members have the formula of C3H6, C4H8, and C5H10. Do these also differ by a CH2 unit? Next page, please. Do you see any relation between the number of carbon and hydrogen atoms in these compounds? The general formula for alkenes can be written as CnH2n, where n is 2, 3, or 4. Can you similarly generate the general formula for alkanes and alkynes? As the molecular mass increases in any homologous series, a gradation in physical properties is seen. This is because the melting and the boiling point increases with increasing molecular mass. Other physical properties, such as solubility in a particular solvent, also show a similar gradation. But the chemical properties, which are determined solely by the functional group, remain similar in a homologous series. Activity 4.2. Calculate the difference in the formula and the molecular masses of A, methanol and ethanol, ethanol and propanol, propanol and butanol. Is there any similarity in these three? Arrange these alcohols in the order of increasing carbon atoms to get a family. Can we call this family a homologous series? Generate the homologous series for compounds containing up to 4 carbons for the other functional groups given in table 4.3. Next topic, 4.2.5, nomenclature of the carbon compounds. The names of compounds in a homologous series are based on the name of the basic carbon chain modified by a prefix, phrase before, or suffix, phrase after, indicating the nature of the functional group. For example, the names of the alcohols taken in activity 4.2 are this one. So I took the names only. So this is methanol. This is ethanol. This is also ethanol. This is propanol because three carbons are there. That makes it prop. And for OH, we will be writing all. So it becomes propanol, right? Here, ethanol. So this is propanol only, sorry, C3H7, and this is ethanol, and this is C4H9OH. This is butanol because it has how many carbons? 4 carbons. Naming a carbon compound can be done by the following method. Identify the number of carbon atoms in the compound. A compound having 3 carbon atoms would have the same name, propane. In case a functional group is present, it is indicated in the name of the compound will either be a prefix or a suffix as given in table 4.4. If the name of the functional group is to be given as a suffix and the suffix of the functional group begins with the vowel A, E, I, O, U, then the name of the carbon chain is modified by deleting the final E and adding the appropriate suffix. For example, a 3 carbon chain with a ketone group would be named in the following manner. You will be writing propane in case carbon are 3. You will be deleting this E, and for because it is possessing the ketonic group, so you will be adding to the remaining word, you'll be adding on. So the name will become propanol. So this is for the ketonic group. If the carbon chain is saturated, then the final name A in the name of the carbon chain is substituted by ene or ine. Unsaturated means either double bond or triple bond. So triple bond and double bond is present in alkene and alkyne. For example, 3 carbon chain with a double bond would be called as propene, and the one which has triple bond will be named as propyne. You need to speak also well and you need to write also well. So for haloalkanes, this table is giving you the nomenclature of the organic compounds. For the haloalkanes, the prefix is chloro or bromo. So here you can see that it is ending in chlorine. So the name has written as chloropropane. For alcohol, the suffix is OL. So here OH has been shown because there are 3 carbons, so the name has become propanol. For aldehyde, the suffix is Al. So 3 carbons are there, but here the ending, the suffix will be Al. So it will be pronounced as propanol. For ketone, the suffix is on. So 3 carbons are there, and notice the ketonic group always comes in between. Aldehyde group always comes in the end. Alcohol always comes in the end. Halogen always comes in the end. So this ketonic group will be known as propanol because how many carbons are there? 3. Carboxylic acid, COOH group will be there at the end. So because 3 carbons are there, it will be named as propanoic acid. Alkenes suffix is going to be ene. 2 double bonds are seen, and it because 3 carbons are there, so name will become propane. Alkyne suffix is ine. See, 3 bonds are there, and because 3 carbons are there, so name will become propyne. In text questions, question number 1, how many structural isomers can you draw for pentane? What are the true properties of carbon which lead to the huge number of carbon atoms as we see around us? What will be the formula and the electron dot structure of cyclopentane? Next, in text question 4, draw the structures for the following compounds: 1. Ethanoic acid, 2. Bromopentane, 3. Butanol, 4. Hexanol. Are structural isomers possible for bromopentane? Question number 5. How would you name the following compounds? So you need to find it out for 1, 2, and 3. 4.3 Chemical properties of carbon compounds. In this section, we will be studying about some of the chemical properties of carbon compounds. Since most of the fuels we use are either carbon or its compound, we shall first study combustion. 4.3.1 Combustion. Carbon in all its allotropic forms burns in oxygen to give carbon dioxide along with the release of heat and light. Most carbon compounds also release a large amount of heat and light on burning. These are the oxidation reactions that you learned about in the first chapter. So this is when you are heating carbon in the presence of oxygen, you'll get carbon dioxide, heat and light. When you heat methane in the presence of oxygen, again CO2, H2O, heat and light. And then you are heating ethanol in the presence of oxygen, it is also producing CO2, H2O, heat and light. So every time the reaction is exothermic. Wajid Khan, welcome to the live reading of carbon and its compound. Activity 4.3. Caution, this activity needs the teacher's assistance. Take some carbon compounds like naphthalene, camphor, alcohol one by one on a spatula and burn them. Observe the nature of the flame and note whether smoke is produced. Place a metal plate above the flame. Is there a deposition on the plate in case of any of the compounds? Activity 4.4, light a Bunsen burner and adjust the air hole at the base to get different types of flames, presence of smoke. When do you get a yellow sooty flame? When do you get a blue flame? The last paragraph, saturated hydrocarbons will generally give a clean flame, while unsaturated carbon compounds will give a yellow flame with lots of black smoke. This results in a sooty deposit on the metal plate in activity 4.3. However, limiting the supply of air results in incomplete combustion of every saturated hydrocarbons giving a sooty flame. The gas kerosene stove used at home has inlets for air so that sufficiently oxygen rich mixture is burnt to give a clean blue flame. If you observe the bottom of cooking vessels getting blackened, it means that the air holes are blocked and the fuel is getting wasted. Fuels such as coal and petroleum have some amount of nitrogen and sulfur in them. Their combustion results in the formation of oxides of sulfur and nitrogen, which are major pollutants in the environment. So every time you are preparing the chapter, you must read this block because a question always can come from these blocks too. Why do substances burn with or without a flame? Have you ever observed either a coal or a wood fire? If not, the next time you get a chance, take close note of what happens when the wood or coal starts to burn. You have seen about that a candle or the LPG in the gas stove burns with a flame. However, you will observe the coal or charcoal in angeeti sometimes just glows red and gives out heat without a flame. This is because a flame is not only produced when gaseous substances burn. When wood or charcoal is ignited, the volatile substances present vaporize and burn with a flame in the beginning. A luminous flame is seen when the atoms of the gaseous substance are heated and start to glow. The color produced by each element is a characteristic property of that element. Try and heat a copper wire in the flame of gas stove and observe its color. You have seen that incomplete combustion gives soot, which is carbon. On this basis, what will you attribute the yellow color of a candle flame to? Samrat, the best question bank for class 10 science is by Rachna Sagar publication. There are two books of it. One is the sample paper, and another is the book that launched in last session only with the name Phygital. It contains lot of questions for each of the student, and there are QR code given in the book. So simultaneously few questions are given, and in case you need to go for more questions, you can scan the QR code and lot many questions will be available for each topic. It has emphasized upon high order thinking skills and case based questions. So Phygital I recommend. Formation of coal and petroleum. Coal and petroleum have been formed from biomass which has been subjected to various biological and geological processes. Coal is the remains of trees, ferns, and other plants that lived millions of years ago. These were crushed into the earth perhaps by earthquakes or volcanic eruptions. They were pressed down by the layers of earth and rock. They slowly decayed into coal. Oil and gas are the remains of millions of tiny plants and animals that lived in the sea. When they died, their bodies sank to the seabed and were covered by silt. Bacteria attacked the dead remains, turning them into oil and gas under the high pressures they were being subjected to. Meanwhile, the silt was slowly compressed into rock. The oil and the gas seeped into the porous parts of the rock and got trapped into water in a sponge. Can you guess why coal and petroleum are called fossil fuels? Next part. Oxidation 4.3.2, activity 4.5. Take about 3 ml of ethanol in a test tube and warm it gently in a water bath. Add a 5% solution of alkaline potassium permanganate drop by drop to this solution. Does the color of potassium permanganate persist when it is added initially? Why does the color of potassium permanganate not disappears when excess is added? You have learnt about oxidation reactions in the first chapter. Carbon compounds can be easily oxidized on combustion. In addition to this complete oxidation, we have reactions in which alcohols are converted to carboxylic acids. Next page, please. So CH3, CH2OH means they are talking about ethanol in the presence of alkaline KMNO4, potassium permanganate and heat, or acidified potassium dichlorate, right? So dichromate, this is the full form of this substance being written here. The chemical formula is K2Cr2O7. So it is potassium dichromate, means this reaction is taking heat, and any reaction that takes heat is endothermic, so it gets converted to the acid, which is acetic acid. Here we see that some substances are capable of adding oxygen to others. These substances are known as oxidizing agents. Alkaline potassium permanganate or acidified potassium dichromate are oxidizing alcohol to acid. So here this is a alcohol because it has functional group OH, and this is acid because it has COOH. Are oxidizing alcohols to acid, that is adding oxygen to the starting material. Hence, they are known as oxidizing agents. 4.3.3 addition reaction. Unsaturated hydrocarbons add hydrogen in the presence of catalysts such as palladium or nickel to give saturated hydrocarbons. Catalysts are substances that cause a reaction to occur or proceed at a different rate without the reaction itself being affected. This reaction is a commonly used in the hydrogenation of vegetable oils using nickel as a catalyst. Vegetable oils generally have long unsaturated carbon chains, while animal fats have saturated carbon chains. So here it has been shown that unsaturation here, because of the double bond, has gone saturated in the presence of nickel catalyst and in the presence of hydrogen. You may have seen advertisements starting that some vegetable oils are healthy. Animal fats generally contain saturated fatty acids, which are said to be harmed for health. Oils containing unsaturated fatty acids should be chosen for cooking. 4.3.4 Substitution reaction. Saturated hydrocarbons are fairly unreactive and are inert in the presence of most reagents. However, in the presence of sunlight, chlorine is added to hydrocarbons in a very fast reaction. Chlorine can replace the hydrogen atoms one by one. It is called a substitution reaction because one type of atom or a group of atoms takes the place of another. A number of products are usually formed with the higher homologues of alkanes. So if you are adding chlorine to the methane, it will become methyl chloride, CH3Cl, and along with that, HCl will be produced. Hydrochloric acid will be produced in the presence of sunlight. In text question 1, why is the conversion of ethanol to ethanoic acid an oxidation reaction? Second, a mixture of oxygen and ethane is burned for welding. Can you tell why a mixture of ethane and air is not used? 4.4. Some important carbon compounds, ethanol and ethanoic acid. Many carbon compounds are invaluable to us, but here we shall study the properties of two commercially important compounds, ethanol and ethanoic acid. Next page now, 4.4.1 Properties of ethanol. Ethanol is a liquid at room temperature. Refer to table 4.1 for the melting and boiling points of ethanol. Ethanol is commonly called alcohol and is the active ingredient of all alcoholic drinks. In addition, because it is a good solvent, it is also used in medicine such as tincture, iodine, cough syrups, and many tonics. Ethanol is also soluble in water in all the proportions. Consumption of small quantities of dilute ethanol causes drunkenness. Drunkenness. Even though this practice is condemned, it is socially widespread practice. However, intake of even a small quantity of pure ethanol or absolute alcohol can be lethal. Also, long-term consumption of alcohol leads to many health problems. Activity 4.4 Teacher's demonstration. Drop a small piece of sodium about the size of a couple of grains of rice into the ethanol. Absolute alcohol. What do you absorb? What will you test? How will you test the gas evolved? So reaction of sodium here, sodium is Na. When it is added to ethanol, ethanol and sodium gets converted to sodium ethoxide. The chemical formula is CH3CH2O Na plus hydrogen gas is evolved. So alcohols react with sodium leading to the evolution of hydrogen gas. With ethanol, the other product is sodium ethoxide. Can you recall which other substances produce hydrogen on reacting with metals? Reaction to give unsaturated hydrocarbon. Heating ethanol at 443 Kelvin with excess concentrated sulfuric acid results in the dehydration of ethanol to give ethene. So when ethanol is heated in the presence of sulfuric acid, it's get converted to ethane. The chemical formula is written here along with water. The concentrated sulfuric acid can be regarded as a dehydrating agent which removes water from ethanol. Now this block which is given at the base. When large quantities of ethanol are consumed, it tends to slow metabolic process and to depress the central nervous system. This results in the lack of coordination, mental confusion, drowsiness, lowering of the normal inhibitions, and finally stupor. The individual may feel relaxed without realizing that this sense of judgment, sense of timing, and the muscular coordination have been seriously impaired. Unlike ethanol, intake of methanol in very small quantities can cause death. Methanol is oxidized to methanol in the liver. Methanol reacts rapidly with the components of the cells. It coagulates the protoplasm in much the same way an egg is coagulated by cooking. Methanol also affects the optic nerve, causing blindness. Ethanol is an important industrial solvent to prevent the misuse of ethanol produced for industrial use. It is made unfit for drinking by adding poisonous substance like methanol to it. Dyes are also added to color the alcohol blue so that it can be identified easily. This is called as denatured alcohol. Next page, please. Now again, a small block. I hope it is visible now. More to know. Alcohol as a fuel. Sugarcane plants are one of the most efficient converters of sunlight into chemical energy. Sugarcane juice can be used to prepare molasses, which is fermented to give alcohol, ethanol. Some countries now use alcohol as an additive in petrol since it is a cleaner fuel, which gave rise to only carbon dioxide and water on burning insufficient air or oxygen. 4.4.2 Properties of ethanoic acid. Ethanoic acid is commonly called acetic acid and belongs to a group of acids called carboxylic acids. 5 to 8% solution of acetic acid in water is called vinegar and is used widely as a preservative in pickles. The melting point of pure ethanoic acid is 290 Kelvin and hence it is often freezes during winter in the cold climates. This gave rise to its name glacial acetic acid. The group of organic compounds called carboxylic acids are obviously characterized by their acidic nature. However, unlike mineral acids, the HCl, which are completely ionized, carboxylic acids are weak acids. Activity 4.7. Compare the pH of dilute acetic acid and HCl hydrochloric acid using both litmus paper and universal indicator. Are both acids indicated by the litmus test? Does the universal indicator it is show them as equally strong acids? Activity 4.8. Take 1 ml ethanol, which is absolute alcohol, and 1 ml glacial acetic acid along with a few drops of concentrated sulfuric acid in a test tube. Warm in a water bath for at least 5 minutes as shown in figure 4.11. Pour into the beaker containing 20 to 50 ml of water and smell the resulting mixture. Next, reactions of ethanoic acid. First is esterification reaction. Esters are most commonly formed by reaction of an acid and an alcohol. Ethanoic acid reacts with absolute ethanol in the presence of an acid catalyst to give an ester. So ethanoic acid, when heated with ethanol in the presence of an acid, an ester is formed. So you should learn and write this reaction. Generally, esters are sweet smelling substances. They are used in making perfumes and as flavoring agents. On reacting with sodium hydroxide, which is an alkali, the ester is converted back to alcohol and the sodium salt of carboxylic acid. This reaction is known as saponification because it is used in the preparation of soap. Soaps are sodium and potassium salts of long chain carboxylic acids. Next step, next page, please. So here saponification reaction is shown to you. Reaction with base like mineral acid, ethanoic acid react with base such as sodium hydroxide to give salt, sodium ethanoate or commonly called sodium acetate and water. So once NaOH is added to acetic acid, then CH3COONA along with water is formed. How does ethanoic acid react with carbonates and hydrocarbonates? Let us perform an activity to find out. Activity 4.9. Set up the apparatus as shown in Chapter 2, Activity 2.5. Take a spatula full of sodium carbonate in a test tube and add 2 ml of dilute ethanoic acid. What do you observe? Pass the gas produced through freshly prepared lime water. What do you observe? Can the gas produced by the reaction between ethanoic acid and sodium carbonate be identified by this test? Repeat this activity with sodium hydrogen carbonate instead of sodium carbonate. Now, this part, reaction with carbonates and hydrogen carbonates. Ethanoic acid reacts with carbonates and hydrogen carbonates to give rise to salt, carbon dioxide, and water. The salt produced is commonly called sodium acetate. So, these are the reactions that are given to you. So, this is acetic acid or ethanoic acid along with sodium carbonate. It is going to give you sodium acetate. And here, sodium ethanoic acid is heated, mixed with sodium bicarbonate, and this is the compound sodium acetate being formed again, along with water and CO2. In text questions, how would you distinguish experimentally between an alcohol and a carboxylic acid? Aditya Sandeep, hi. Welcome to my channel in this live reading of Chapter 4, Carbon and its Compounds. So, how would you distinguish experimentally between an alcohol and a carboxylic acid? What are oxidizing agents? Activity 4.10, soaps and detergents. This is the topic under this activity has been given to you. Take about 10 ml of water each in two test tubes. Take a drop of oil, cooking oil, in both the test tubes and label them as A and B. To test tube B, add a few drops of soap solution. Now shake both the test tubes vigorously for the same period of time. Can you see the oil and water layer separately in both the test tubes immediately after you stop shaking them? Leave the test tubes undisturbed for some time and observe. Does the oil layer separate out? In which test tube does this happen first? Aditya, this is the recording for the audio book, okay? So I will be starting the explanatory videos in my life. A notification will definitely reach you. In case you find my channel helpful, you can subscribe to it so that you can get the notification. This is the recording for the audiobook. This activity demonstrates the effect of soap in cleaning. Most dirt is oily in nature, and as you know, oil does not dissolve in water. The molecules of soap are sodium or potassium salts of long chain carboxylic acids. The ionic end of soap interacts with water, while the carbon chain interacts with oil. The soap molecules thus form structures called micelles, as shown to you in figure 4.12, where one end of the molecule is towards the oil droplet while the ionic end faces outside. This forms an emulsion in water. The soap micelle thus helps in pulling out the dirt in water, and we can wash our clothes clean. Figure 4.13. Can you draw the structure of a micelle that would be formed if you dissolve soap in hydrocarbon? So the next heading is micelles only. I hope the screen is readable now. So soaps are molecules in which the two ends have different properties. One is hydrophilic, that is interact with water, while the other end is hydrophobic, that is it interacts with hydrocarbons. When soap is at the surface of the water, the hydrophobic or the tail of soap will not be soluble in water, and the soap will align along the surface of the water with the ionic ends in water and the hydrocarbon tail protruding out of water. Inside water, these molecules have a unique orientation that keeps the hydrocarbon portion out of the water. Thus, clusters of molecules in which the hydrophobic tails are in the interior of the cluster and the ionic ends are on the surface of the cluster. This formation is called a micelle. Soap is in the form of a micelle is able to clean since the oily dirt will be collected in the center of the micelle. The micelles stay in solution as a colloid and will not come together to participate because of ion-ion repulsion. Thus, the dirt suspended in the micelles is also easily rinsed away. The soap micelles are large enough to scatter light, hence a soap solution appears cloudy. Activity 4.11. Take about 10 ml of distilled water or rainwater and 10 ml of hard water from a tube well or hand pump in separate test tubes. Add a couple of drops of soap solution to both. Shake the test tube vigorously for an equal period of time and observe the amount of foam formed. In which test tube do you get more foam? In which test tube do you observe white curdy precipitate? Note for a teacher: if hard water is not available in your locality, prepare some hard water by dissolving hydrocarbonates, sulfates, chlorides of calcium or magnesium in the water. Activity 4.12. Take two test tubes with about 10 ml of hard water in each. Add 5 drops of soap solution to one and 5 drops of detergent solution to the other. Shake both the test tubes for the same period. Do both test tubes have the same amount of foam? In which test tube is a curdy solid formed? Just wait. This has come to the first page. I'm just reaching where I was reading. So we have already read this and we were on activity 4.12. So this has already been done. Have you ever observed while bathing that foam is formed with difficulty and an insoluble substance scum remains after washing with water? This is called this is caused by the reaction of soap with the calcium and magnesium salts, which cause the hardness of water. Hence, you need to use a large amount of soap. This problem is overcome by using another class of compounds called detergents or cleansing agents. Detergents are generally sodium salts of sulfonic acids or ammonium salts with chlorides or bromide ions, etc., but have long hydrocarbon chains. The charge ends of these compounds do not form insoluble precipitates with the calcium and magnesium ions in hard water. Thus, they remain effective in hard water. Detergents are usually used to make shampoos and products for cleaning clothes. Next block, in text questions. Would you be able to check if water is hard by using a detergent? 2. People use a variety of methods to wash clothes. Usually, after adding the soap, they beat the clothes on a stone or beat it with a paddle, scrub with a brush, or the mixture is agitated in a washing machine. Why is agitation necessary to clean the clothes? So that was all in this chapter. Once you are done with the reading, just go ahead with the summary so that you should not leave any point. So here is the summary of carbon and its compound, chapter 4, class 10th, science. Carbon is a versatile element that forms the basis of all living organisms and many of the things we use. This large variety of compounds is formed by carbon because of its tetravalency and the property of catenation that it exhibits. Covalent bonds are formed by the sharing of electrons between two atoms so that both can achieve a completely filled outermost shell. Carbon forms covalent bonds with itself and other elements such as hydrogen, oxygen, sulfur, nitrogen, and chlorine. Carbon also forms compounds containing double and triple bonds between carbon atoms. These carbon chains may be in the form of straight chains, branch chains, or rings. The ability of carbon to form chains give rise to a homologous series of compounds in which the same functional group is attached to carbon chains of different length. The functional groups such as alcohols, aldehydes, ketones, carboxylic acid bestow characteristic properties to the carbon compounds that contain them. Carbon and its compound are some of our major sources of fuels. Ethanol and ethanoic acid are carbon compounds of importance in our daily lives. The action of soaps and detergent is based on the presence of both hydrophobic and hydrophilic groups in the molecule and this helps to emulsify the oily dirt and hence its removal. So we are done with the reading of carbon and its compound, chapter 4, class 10 science, taken from NCERT. In case you are interested in hearing the audio further, you can replay and you can share it with your friends. Thank you. See you in next video.